Hello, Mr. Simpson here with the video for Chapter 3, Section 5, Periodic Variations in Element Properties. You can see the learning objective is listed here. This section we are going to focus on what are commonly known as periodic trends. So there's many properties that change in a very predictable and systematic way as you move through the periodic table, horizontally across a period or vertically down a row. The properties we're going to talk about in this video are size or radius of both atoms and ions, ionization energy, and electron affinities. Before we get into the different periodic trends, I'd like to introduce you to a concept known as effective nuclear charge, or sometimes referred to as ZEF. This is the pull exerted on a specific electron by the nucleus, taking into account electron-electron repulsions. We talk a lot about the force of attraction between the negatively charged electrons and the positively charged nucleus. We don't often think about the repulsion that occurs between electrons themselves. So as we discuss the valence electrons, or those electrons in the outermost energy level, we have to understand that there are also a group of electrons between those valence electrons and the nucleus. And those like-charged repulsions between negatively charged electrons are going to have an effect on the force of attraction between the nucleus and the electrons. Here in the notes, we talk about hydrogen. So hydrogen, there's only one electron, so there are no core electrons that are having that repulsive effect on the outermost valence electron. So the nuclear charge and the effective nuclear charge are essentially the same. For all other atoms, the outermost valence electrons are shielded from the pull of the nucleus by other electrons present. This is an important concept to keep in mind as we talk about the relationship and these properties, because in many cases we're going to be talking about the effect of the valence electrons and its attraction to the nucleus. Okay, so let's jump into size or radius. So what we want to do is understand first what the definition of the trend is, then make sure we understand how that property is going to change as we move down a group or across a period. And then finally, we want to be able to predict which atoms would have, in this case, the larger size or smaller size. And this is often referred to as atomic or ionic radius. All right, so let's talk about the trends down a group and across a period. And I have some examples here that we will look at in a second. Okay, so down a group, as I move down a group on the periodic table, the big change that's occurring here is I'm adding energy levels. So we know as we look at our periodic table here, the numbers of the energy levels 1 through 7 are down the side. So as I transition down a group, I'm adding a new energy level. And we also know at this point that those energy levels are getting further from the nucleus. So it should be pretty self-explanatory that as I move down a group, atomic size is going to increase. Okay, so the distance between the nucleus and the outermost valence electron, that's the definition of atomic size or radius. That will increase as I move down a group because I'm adding energy levels, and those energy levels are getting further from the nucleus. Across a period isn't quite as simple as down a group, and I'm actually going to reference Coulomb's law here to help us understand what happens as I move across a period. So if you recall, Coulomb's law, the basic setup of it is the force of attraction or repulsion is based on the charge of the two objects over the distance squared. So the force of attraction, in this case, let's talk attraction because we're talking negatively charged electrons and the positive protons in the nucleus. The force of attraction is going to increase as I add more charge, more positively charged protons and more negatively charged electrons. And that relationship is going to be inversely proportional as I change the distance. So the further away I get, the force of attraction is going to decrease. So now let's think about what happens as I move across a period. So I'll just jump right here in period 3. As I move across this period, I am not changing my distance from the nucleus because I still have electrons. The furthest electrons away are in the third energy level. But what I am doing is adding protons and electrons. So I'm adding charge, and that charge is not getting any further away from one another. So what that would mean is that the force of attraction is going to increase slightly as I move across and go from 13 protons and electrons to 14 protons and electrons to 15 protons and electrons. So you can see as I move across a period from left to right, if my force of attraction increases, that means it's going to pull those valence electrons a little closer each time. So across the period for size, the trend is to decrease. As I said at the beginning, 3 steps here. Step 1, understand the trend, the definition of the trend. So for radius or size, it's distance from the nucleus to the outermost electron. Understand how that property changes systematically as I move through the periodic table. So hopefully you can explain why it increases going down a group and decreases going across a period. And finally, apply that to determine which in a series of elements would have the largest size or the smallest size. So I've listed 4 elements here: carbon, aluminum, oxygen, potassium. So if we were asked which of these is the largest or has the greatest atomic radius, you would take a look, identify where these atoms are located. So here's carbon, aluminum, oxygen, and potassium. Okay, now when I'm looking at numerous atoms like I am here, it really helps to focus in first and foremost on one trend. So in each of these, there's going to be a trend that's the more dominant or more significant change. In this case, for radius, it's the vertical trend. So adding an energy level as I move down a group is going to be a more significant change than adding charge and gradually changing the force of attraction. So in this case, if I were looking for the largest atom, I would just look for which atom initially is lower on the periodic table. So in that case, clearly the answer here is potassium. Potassium has electrons in the 4th energy level, so that would be further away. Granted, if I were to look only at the horizontal trend, you can see, it would look to me as though potassium, way over here on the left, would be the smallest of the 4 atoms. But again, the dominant trend here for atomic radius is the vertical trend moving down a group. Okay, when we talk about radius, we also should talk for a second about ionic radius. So obviously this is used to describe the size of an ion as opposed to an atom. A cation always has fewer electrons with the same number of protons, right? Cation means positive ion, so we're losing electrons. As those electrons are removed, the remaining electrons will have a greater Zeph, right? So the core electrons would now outnumber those valence electrons because I'm losing valence pretty significantly. I'm losing valence electrons. So those are drawn even closer to the nucleus, those valence electrons. So a cation is always smaller than the atom from which it was derived. I can think about the exact opposite effect when discussing an anion. So an anion is going to have more electrons than protons. That anion, so those valence electrons would outnumber the core electrons more, and there would be less of an effect of Zeph, which means that the anion would be larger than the atom from which it was derived. We've heard this term already, but just to reiterate, because this happens when talking about periodic trends, atoms and ions that have the same electron configuration are said to be isoelectronic. If you have an isoelectronic atoms or ions, the protons really is what determines the size here. So for example, if I go back up to our periodic table here, and let's say that I was trying to compare K plus ion, cation, the chlorine anion, and argon atom. Okay, so if I take a look at these, you're going to see this is an isoelectronic series. All of these would have 18 electrons. Okay, what's different with all of these is their number of protons. So potassium would have 19 protons, chlorine anion would have 17, and the argon atom would have 18. Okay, so now if I'm thinking about, and this is I think also where Coulomb's law helps here, if I was looking for the largest atom, well, let's switch it. Let's talk about the smallest atom this time, or the smallest size, atomic or ionic. If I look here, we talked a second ago, now it's going to depend on the number of protons. So thinking about which of these three would, if I'm talking smallest, have the greatest effect on pulling those 18 electrons closer to the nucleus, hopefully you could identify that the potassium cation with 19 protons is going to pull those 18 electrons closer to the nucleus than the chlorine anion with only 17 protons, or even the argon atom with only 18 protons. Let's move on to the next trend, which is ionization energy. So ionization energy in general is the amount of energy required to remove an electron from an atom. Atoms don't just lose one electron, they can lose multiple electrons. Therefore, there are multiple ionization energies. So the ionization energy required to move the first electron is called the first ionization energy, and then the next electron would be the second ionization energy, and so on. With regards to successive ionization energies, those are always going to increase. So after I remove one electron, the second ionization energy is going to be higher. It's going to require more energy to remove that second electron. Now, in some cases, we can predict that it's going to be very small, or maybe even just looking at the periodic table may predict that it's going to go down. And then in some cases, we can predict a large jump in the ionization energy. So let's think about the trends here. Now that we know what the definition is, let's think about what those trends are. As I move down a group, again, same concept here. The significant thing that happens as I move down a group on a periodic table is I'm adding energy levels. And so therefore, the valence electrons are getting further from the nucleus, and that force of attraction becomes more difficult. So as I move down a group, ionization energy is going to decrease moving down a group. As I move across a period, one of the things that helps here is thinking about the octet rule. Okay, so we know that all the atoms in the periodic table here are trying to fill their octet. They're trying to get the same electron configuration as the noble gases. So if I'm over here at group 7, these halogens all have 7 valence electrons. So they're only 1 electron away from filling their octet. So the chances that they are going to give an electron up easily and get actually further from the filled octet are slim, which means I have a high ionization energy over here. It's going to require a lot of energy to remove electrons as I get over here closer to the noble gases. On the other side, I have elements with one or two valence electrons, and these atoms are trying to donate or give up their valence electron in order to get rid of that valence shell and drop down to the filled core electrons beneath it. So over here on the left, we're going to have very low ionization energies. Now, along those lines, let's talk a second about the difference between first and second ionization energies. Let's just talk about sodium for a second. Sodium is going to have a low first ionization energy because it's over here on the left with only one valence electron. So it's going to be fairly easy to remove that one valence electron. It's not going to require a lot of energy. Now, after that, its second ionization energy, the removal of its second electron, is the amount of energy is going to jump significantly, because now, after we remove one electron, we now have the same electron configuration as a noble gas. So you can see the relationship here between ionization energy 1 and the first ionization energy and the second ionization energy. Sometimes you get a really large jump in those values, and that's a good illustration. Okay, so back to our trend for a second. So we said down a group it's going to decrease, and across a period it is going to increase. Okay, and then we just have to also make sure that we are specific about if we're talking about the first ionization energy or second ionization energy, because that will change exactly where we are and what electron we're looking at. So let's look at an example here. If I wanted to know which of these two atoms would have a higher first ionization energy, Okay, so here's the application part. So there's my lithium. Get rid of this circle so we don't get confused what we're looking at. And here is my cesium. Okay, so ionization energy, we said, decreases as we move down a group. So lithium would have the higher first ionization energy. The last trend here is electron affinity. You see the definition of electron affinity. It's basically the opposite of ionization energy, where we're talking about the energy change for the process of adding an electron to form an anion. Unlike a radius and ionization energy and even electronegativity, which we'll talk more about when we get into covalent bonding, electron affinity, you do not often identify the same systematic changes as we move through the periodic table. It's listed as a periodic trend because there are, to some degree, some changes that we can predict, but you're not going to see the same examples like I showed you in the first two trends for atomic radius, identifying which would be larger or smaller, higher ionization energy or lower. So for electron affinity, let's just make sure we understand the definition of electron affinity at this point. Okay, that wraps up this section.